remote tower and on virtual center. The last one was a week ago. And we are having now 2 sessions on CNS. So the first one is more with a holistic view on CNS, and the second one zooming in on specific technological innovations. After that, we'll still have this year one on use-based consolidation, on trajectory-based operations, and probably a few on specifically zooming in on the different aspects of environmental improvements. Just on the household side of things, I guess I see already lots of chats coming in, so you've probably discovered on the right side that there is a tab with the chat button, but there is also another tab with questions. And I would like to invite you as audience to, whenever you have any question, just put it in the questions tab, not in the chat. And as the speakers will keep an eye on it, we'll be able to answer them online. But also we have at the end of this session half an hour for question and answers, which we'll discuss in this online panel. So whatever is not going to be answered in the online version, we'll discuss verbally. And if that is not answered, we'll still recap and gather all any missing answers later on for publishing on the website. So today's speakers, we have, first of all, on CNS evolution, Emilia Robert from Eurocontrol, then safety-driven technical performance by Esther Delgado Pinedo from Indra, resilience in CNS by Okwari Osechas from DLR, and spectrum in aviation by Gerard Bertz, or Gary, from Eurocontrol. And before I give the floor to you, Emilia, I will read out your bio, if I can find it. Yes, okay. So, Emilia Robert joined Eurocontrol in 2010 as a navigation expert. Since 2014, he's leading the integrated CNS SESAR solutions and has been working on the evolution of CNS, and in particular on the development of an integrated CNS roadmap. Emilia, the floor is yours.
Good morning, and thank you, Ruben, for the introduction. This morning, I will talk about the CNS evolution and mainly the integrated CNS concept, which has been developed in SESAR in the last few years. So, let's start with integrated CNS concept. At the beginning of ComNav and surveillance some decade ago, they were completely independent for good reason, for safety reasons. The idea was if an aircraft was losing its navigation, then using surveillance from the ground and the connection with the ADCO was able to lead him to his destination. That was the safety concept of having 3 different independent infrastructure and applications. However, a few years ago, a newcomer made his entry into the CNS world. It's mainly the GNSS, which is already shared by navigation and surveillance. It's used by navigation to navigate, and it sends its position for ADS-B to the air traffic controller. And that created a link between the 3 domains. Following these evolutions, we created the integrated CNS concept, where the idea was to consider this link between domains and to work with them. So integrated is sometimes a word which is not fully understood. Some people think that it's about having one single infrastructure and one single equipment on board for the 3 applications, which will raise some safety concern, I fully understand. It's not exactly what it is. It could be in the future. It could be in the long-term future that we will have one single system with the right safety study about it. But for now, it's more about considering the domain as one domain, identifying the opportunity between domains, reinforcing the robustness between domains, and having a common evolution of the 3 domains. So sometimes integrated is not always the good word. I think maybe common would be a better word, but that's what we have for today. So in SESAR 1, we identified this concept, and we thought that they will be supported by 4 different pillars. The first one is to identify the robustness and opportunity of the infrastructure when we consider ComNav and surveillance as one domain. The second one was to identify that we could put the different individual performance-based concept into a common framework, a performance-based CNS framework concept. You can see the second red rectangles on the top. And all of this will need to evolve with a common strategy, with a common roadmap. And this is where we need an integrated CNS roadmap strategy. And of course, we need a common civil military synergies for all of them. And this is the reason why in SESAR 1, we had this main 4 deliverables supporting being the 4 pillars of this concept. And today we'll mainly discuss about the CNS evolution roadmap. We started this roadmap with a top-down approach following the SESAR visions. The SESAR has been working on a document and prepared a vision for the evolution of CNS around 8 strategic directions. The first one was to increase digitalization, connectivity, providing a higher automation level. We also want a new to implement a safe, secure, and resilient infrastructure. There was this vision to move from physical asset management to CNS services, to develop, as I explained, a performance-based and integrated CNS concept, to combine the data from the satellite-based infrastructure and the ground-based infrastructure. We also need in the future to rationalize the legacy infrastructure, increase the military synergies and values, and of course, last but not least, ensure an efficient and long-term availability of suitable spectrum. I think we all agree with these 8 directions. They are very good. We all think, I guess, that they will be beneficial for CNS. But once we have said that, we haven't said what we are actually going to do. So that's where the bottom-up approach kicked in. For the development of a roadmap, we also consider a bottom approach when we consider COM-NAV surveillance as a first separate entity and identify what are the current evolution of the system. For voice, for COM, we have today a system where the voice is primarily supported by data link. In the future, this might move with a big development around the multi-data link, most likely based on Aeromax, VDML2, LDAX, and SATCOM-B. For navigation, it's mainly conventional plus inertial today, where we are going to move toward a more use of geofrequency and multi-constellation GNSS for the 3 domains for SBAS, ABAS, and GBAS. And for surveillance, we'll have a similar trend. We're going to move toward the composite surveillance domain, mainly based on ADS-B and ground-based ADS-B and space-based ADS-B supported by MLAT and ODES cluster. We put all of this different evolution in a document called supporting materials. And the idea of this work was to identify what is the pipeline today. Aviation is a slow-moving animal, and nothing is certified and in use before 10 years. When start developing a system, it needs at least 10 years to be certified. So if you want to see what's going to be there in 10 to 15 years ahead, looking at what is being developed today is the best way to have a fair view on these evolutions. But that's the idea of this bottom strategy. And then we combine these 2 approaches, the bottom and the top-down, to develop the roadmap. And this combination led to stress the need for an integrated CNS concept. We need to consider COM-NAV surveillance as one domain. And again, on system that it's one domain, it's not one system, but it's one domain. Generalize the concept of a minimum operational network. This concept has been brought by the FAA to define the evolution of a VOR network. And the idea is to generalize this concept to the world CNS infrastructure. And we'll come back to that. Definition of a target architecture. By target architecture means it's the light at the end of the tunnel. This is where we want to go. That's the objective. Development of a transition path, how to go to this target. And at the end, identification of the rationalization opportunities along the way to meet this target. So we started from this concept of integrated CNS, and we developed, as I explained, a target architecture. I will come back on the next slide, but it's many, you can already see on the slide that it's mainly composed of 3 layers. At the bottom, at the very bottom, you have a spectrum, which supports all our applications. And then if you go up, you have a congenerialization of a minimum operating network for the legacy infrastructure, which supports the backbone of a future infrastructure composed mainly of secure CNS services. And at the top, you have a performance-based application for the 3 domains. And at the last layer at the very top are the air traffic services. And we develop a transition path, how to go from today's situation to the target architecture. So let's move to this target architecture. There is a lot of things on that picture, but I would like you to focus on three things. It's composed of three layers, as I explained before. At the top, you have a performance application group under a common CNS performance-based framework. Today we have PBCS for COM, PBN for NAV, and PBS for Surveillance, which is being developed, complemented by the performance-based aerodrome operating minimas. These applications are supported by a backbone of a future infrastructure in the form of CNS, in the form of secure CNS services, mainly composed of multi-data link, dual frequency multi-constellation GNSS, ADS-B, both space and ground, and advanced airborne capability, also complemented by the swim technical infrastructure. And at the bottom, it is supported by a layer of minimum operating network, which is a fair rationalization of the current infrastructure that we have today. If we now move to the CNS transition path, it's a big picture. There is a lot of things on this picture, but it's not so difficult to read. Each arrow represents a technology and how this technology will evolve, and each rectangle on top of the arrow is the application that is supported by this technology. So it's very convenient. If you look at one particular applications, you can see which technology is supporting these applications, and you can see when this technology needs to evolve to support the applications. However, to simplify the reading of this picture, I would like to highlight two items. The first one is what we call the 2025 rendezvous. It's somewhere around 2025. We have these big evolutions, which are already on bottom approach, where we have for COM a multi-data link environment based on the Delmo 2, LDAX, Aeromax, and SATCOM. We will bring together the composite surveillance, and navigation will mainly be based on DFMC GNSS. That's the first item to consider. The second thing to consider is that we are going to move towards a more performance-based environment, what we call performance-based CNS. It could be three individual concepts together under a very light framework on something more integrated, and we'll come back to that on a later slide. And at the very end of this picture, you can see the definition. Sorry, you can see the definition of the objective infrastructure. So we really see the path from today's situation towards this objective infrastructure. Rationalization opportunities. There's a lot of opportunities along the way. Again, if we put on the figure the 2025 rendezvous, we can see that it's really the beginning of a lot of personalization that is being foreseen, or it will help us in rationalization further. So this rendezvous is really important for this aspect. It either allows us to better rationalize or to reinforce rationalizations. Let's come back to performance-based CNS. Today we have three individual concepts. For communication, we have PBCS, which is kind of a mix of communication and surveillance. We have a PBS concept being developed today, and the PBN concept for navigation, which is well mature, already in place in lots of environments. The idea of this performance-based CNS is to provide a common framework to these different concepts and to bring them together. Now, the level of integration may vary. It could be something very light. It could be something more present. It will all depend on how these three different concepts evolve together and how fast they converge from one to another. In wave one, we had a bottom approach to performance-based CNS. We first identify the different concepts. Then we identify all the different applications for the different phases of flight and put them into a single chart. That was the first item we did. You can see the result on the left-hand side of the slide, where we have for COM, NAV, and surveillance. We have a first classification for COM, it's data and voice, which I think makes sense. For navigation, it's RNP and RNAV, which are two different flavors of PBN. And for surveillance, we have cooperative and non-cooperative, which are again a big classification in the surveillance domain. And for each of these subclasses, we have the infrastructure layer and the application supported by the infrastructure. So by identifying all of this, we are able to make a comparison between the different domains, identify similarities, differences, and start to pave the way for a future convergence of the three domains. And on the picture, it's color-coded either by applications for com, nav, and surveillance, or for the infrastructure. It's color-coded following the target infrastructure for the CNS backbone, for the MON, and for independent airborne capability. And Esther will come back to this picture later on. So we did this work in the wave 1 of SESAR between 2016 and 2019. All of the content of this roadmap and of this concept has been captured into the European Master Plan 2020. It's not in the slide, but has also been captured into the airspace architecture study. So in these two documents, you will see maybe different form of the figure that I presented today, but the content is exactly the same. It's fully aligned. We have the exact same content in these two documents. And the idea for wave 2 is to further develop this concept. We have already identified a list of items in which we need to improve our vision on the CNS evolutions. The first one is to further develop the concept of CNS services, which is linked with the definition of the air traffic data service provider. Update the spectrum considerations. Update the drone considerations, which will improve it. Develop a cybersecurity sections because we want to develop secure CNS services. So cybersecurity is an item. Improve the airborne aspect. And a global update we always need to do. It's already the end of my presentation, so I will go for summary and take-home messages. On the right-hand side, again, you can see the picture of this target infrastructure. I really would like to insist on that. If there is something that we want to keep from my presentation, is this picture of the target infrastructure. Again, in 3 years, with a fair rationalization at the bottom, the backbone of future infrastructure in the form of secure CNS services and the performance-based applications. And the way to go there is first to rationalize our current infrastructure. We can start today. And we are starting today in CNS. It's being started. Then to develop further the CNS services. And this is linked with this new concept being developed in the airspace architecture study, the ATM data service provider. And to further develop or further provide a common framework for the individual first CNS concept, and in the future, a common approach to performance-based CNS. And again, as highlighted before, all of this will be reinforced, sometimes enabled, sometimes supported by this 2025 rendezvous with the development of a multi-data link, the composite surveillance, and the DFMC GNSS. My presentation. Thank you very much. And if you have any questions, I'll be very happy to answer.
Thank you very much, Emilia. I do see questions already coming in, but for now, I think it's better that we save them till the end, because I suspect that some of the questions will be answered by future presentations. Let me continue with introducing the next speaker, Esther Delgado-Pinedo. So a bit of a background here. Last week, we were confronted with a last-minute change on one of the speakers. We had originally scheduled Miguel Munoz, who unfortunately had to withdraw due to other commitments. And I'm very happy that Esther Delgado was available and willing to take over from Miguel at the very last minute. Esther is a systems engineer at Indra. She's been an active member of SESAR 2020 Wave 1, focused on Project 14, Essential and Efficient Communication, Navigation and Surveillance Integrated Systems. She's currently involved in Wave 2, same project, I would say, still Project 14, focusing on integrated CNS. Esther, the floor is yours. Can you put it in the presentation mode, please?
Yeah. Okay. So good morning, everyone, and thank you, Ruben, for the presentation. Today I'm going to present the safety-driven technical performance presentation. And first of all, I would like to introduce the PBCNS concept a little bit. Performance-based communication, navigation, and surveillance are being developed, allowing the ATM CNS to evolve from a system-based operation towards the delivery of CNS services in a technology-agnostic manner. These CNS services are no longer oriented to technology, but to a PBCNS environment. Focus on the operational objectives and needs identified, the PBCNS standards are derived. And these standards aim at achieving these operational objectives based on safety, capacity, efficient, and environment. As an example, we can focus on the surveillance domain, for example. Previously, the standards were produced for each sensor individually. The ED129, the EuroCAE standard for ADS-B, or for example, the ED142, the EuroCAE standard for the wide area multilateration. In response to the PBCNS needs, the Gensur SPR is being developed. This document determines the minimum requirements for a generic surveillance system and links the ATC surveillance services, the environment types, the separation minima, with the corresponding requirements on cooperative ATC surveillance data provision. So, as already presented by Emilian in the previous presentation, this slide is obtained from the SESAR 2020 Wave 1 Project 1411, showing the progress of the PBCNS framework. As you can see, the development is not homogeneous. PBN has much more development at the moment than PBCS. The PBCNS framework scope is also very different for each of the domains at this time. Performance-based communication and surveillance is a newer concept, and it's still being developed to give a solution to the existing operational needs. It started focusing on the oceanic area, and it's now spreading to the other airspace types. As you can see, it's a little bit tiny, but in the picture, the surveillance infrastructure has been extended to the oceanic environment with the use of the space-based ADS-B. But in the case of communication, the use of technologies could continue to help reduce separation and take the advantage of the full potential of the space-based CNS. So in this slide, we can see an example, a clear example of the use and benefits of implementing this performance-based communication and surveillance framework, looking at the ICAO performance-based separation. Before using this approach, these were the minimum allowable separations for oceanic environments according to ICAO. The operational need was clear. They wanted to increase the capacity in those airspace while maintaining the same safety levels. So from this need, a new PBCS framework was produced for oceanic areas in order to enable a separation minima reduction. As you can see in green, from 10 November 2016, certain separation minima shall be applied only to those pairs of aircrafts meeting RCPs and RSPs specifications. The Asian Pacific and the North Atlantic regions agreed to transition to the implementation of these new requirements from March 2018 in part of the airspace. And the operators need to obtain a PBCS operational authorization for applicable RCPs and RSPs in order to apply them and benefit from them. So moving on, we are going to talk about the SALSA project. The SALSA project was funded by SJU. Ending in 2018, it focused on the challenge for the separation minima revision and the opportunities for enhanced surveillance in the non-radar area enabled by the satellite-based ADS-B. So according to SALSA and also to ICAO separation and airspace panel view, 15 to 18 nautical miles standard could be possible using satellite ADS-B and the current SATCOM, RCP 240. They concluded that the separation depended on the precision of the aircraft position report and on the latency of communications. Also, according to SALSA, the reduction of the separation minima in the oceanic areas to the limits applied to the radar areas in continental airspace, like 3, 5, or 8 nautical miles, requires a level of sensor redundancy and a direct voice communication VHF-like. So when combining satellite ADS-B and satellite VHF voice-like, it is possible to provide a reduction on the current separation minima in non-radar areas, as well as to improve the safety of the ATC operations. SALSA also pointed out that the need to define that there was a need to define new potential separation standards and separation management techniques in the non-radar areas, and also pointed out that existing RCPs and RSPs could be extended for reduced separation. So all in all, this is a great example showing that the studies are concluding that RCP could be improved by the use of satellite communications VHF-like, as for example, satellite-based VHF or NGEN-SATCOM. So in another study, this one is from the FAA, they were focusing on the use of ADS-B or ADS-C in the North Atlantic oceanic areas, Gander and Sandwich oceanic airspace. And it was observed that the limits of separation were again limited by RCP 240. If we have a look at the paper, we could see that the smaller separations are achieved by improving the surveillance, thanks to the use of new technical enabler ADS-B satellite. But still, since the RCP does not improve, lower levels of separation cannot be reached. So as a conclusion, achieving a lower RCP could lower the minimum separation required. And the focus has to be put in developing these new RCPs, opening up the need for new technologies to achieve them. So in this slide, we are going to see how is the process to implement the performance-based approach that I've been talking about. The first step for implementing the performance-based approach would be to identify which is the new operational need being pursued. For example, for the definition of the oceanic RCPs and RSPs of ICAO, the operational need was clear, was to achieve a reduced minima separation in the oceanic airspace. The second step would be to convert the operational need into a plan. This is where this is the part where the CNS challenge is set. Here it's about defining what has to be improved in order to achieve the previously established operational need. Again, going to oceanic example, SALSA project concluded that the separation minima was dependent on the precision of aircraft position report and of the latency of the communications. So, improving these parameters, we can reduce the required minimum separation. After that step, a safety risk assessment is required. This safety risk assessment needs to be performed simulating the worst cases scenarios for the study case. It has to take into account, for example, the different aircraft speeds, the types of aircrafts, the traffic mix, and so on. After that, from this safety risk assessment, the performance-based requirements would be obtained. This is the case for the ICAO Oceanic Performance-based separation. If you recall, where they obtained the RSP 180 and the RCP 240 from this safety risk assessment. After we have obtained the performance-based requirements, it is time to implement the solution and obtain the operational benefits. And the last step, which is a continuous step, it's important to carry out a continuous monitoring of the required performance. And in case of detecting a degradation trend, act to maintain the safety level. So I wanted to give you an example of what I just explained, and I have prepared this example applied to the performance-based surveillance. So in this case, what was intended was to reduce the separation from 2.5 to 2 nautical miles of separation between approaching aircrafts, obtaining a greater capacity for the airport. So once the operational needs are identified, they are converted into a plan. As you can see here, it is suggested that the update rate of the position needs to be reduced in order to obtain the operational benefit. So a safety assessment is carried out where the worst case scenarios are simulated for different traffic mix using different update rates and different surveillance error assumptions. Once done, the performance-based requirement to sustain the separation of 2 nautical miles in approach are obtained. As you can see, they are obtained as a function of the maximum time that may exist between updates in seconds and the maximum error in the surveillance position report in meters. The requirements are not associated with any technology, so they are technology agnostic, which means that can be fulfilled by any of the surveillance technologies available, as long as the required performance are met. In the example, this is a typical application that a WAMP system could fulfill, but using the performance-based surveillance approach, it could also be done with a secondary radar rotating faster, as you can see in the image. So in this way, the operational need is satisfied, and the next point would be to implement the technology meeting these performance requirements, and of course, the continuous surveillance performance monitoring, identifying the degradation trends early using offline or quasi-real-time monitoring, and using, for example, the surveillance performance monitoring tools developed within the SESAR framework. And to end this presentation, I would like to present the main operational benefits that the performance-based approach enables. First of all, safer operations. As for example, as we have already mentioned in the oceanic airspace, enabled by the reduced latency in communications and more precision in position reports. Also, it enables ANSPs and operators to expand their businesses globally while rationalizing terrestrial infrastructures. Also to make possible for airlines to select their preferred routes in order to optimize flight time and fuel consumption, including the need for aircraft to carry extra fuel. Another one would be the redesign organized track systems, offering people more and shortened routes with higher levels of quality of service and punctuality. And last but not least, reduce CO2 emissions to highly contribute to the global environmental goals of the aviation industry, thanks to the benefits of the points mentioned before. And with that, I finish my presentation. And if you have any question, please feel free to ask me.
Thank you very much, Esther. That was really appreciated. You're also well on time. I think we're only 4 minutes behind schedule. That's probably because I took the first 4 minutes when I did the introduction. Meanwhile, I do see lots of questions coming in. They are triggered by the first two presentations so far, but I suspect that all of the speakers have an opinion on or have an answer to that. So please already have a look and see if you can type anything in already. I also would like to point out before I introduce Okwari here that I do see quite a couple of questions coming in on VHF voice, on satellite-based voice, etc. Like to raise your attention that to the fact that the next CNS session will have a dedicated topic on digital voice over IP air-ground as well. So that will zoom in much more into the voice over IP aspects. This was a bit complementary to what Esther presented here on VHF satellite-based. Introducing the next speaker, Okwari. I'm going to make you big for a moment. So Okwari is a researcher with the German Aerospace Center DLR. He has received a PhD from Tufts University in Boston, Massachusetts in 2014. Back then, he focused on integrity monitoring for GBus. He joined DLR in 2015 and has been active in alternative positioning, navigation, and timing, PNT, ever since. In fact, his team leads the APNT solution in current SESAR Wave 2 Project 14. More recently, Okwari has started becoming more active in the topic of resilient CNS systems, in particular making aviation more resilient to outages in satellite navigation. I can see you smile. You're enthusiastic, which is great. So the floor is yours.
Thank you, Ruben. What do I do here? I put this part big. Now everybody can see my slides, right?
Yes, perfect.
Good morning, everyone. Really appreciate your interest in this. Thank you for being here. And thank you for the introduction, Ruben. My name is Okwari Osechas. I'm here to talk a bit about resilience in CNS systems. It should be pretty evident that the challenges in CNS are changing. There are a lot of there's a lot of talk of challenges in performance. We have disruptions of GNSS from ionospheric activity. There's a lot of scientific work on that. I don't need to tell anyone in this webinar series that that UAS presents a very interesting challenge for CNS. But there's a very different type of challenge that we need to look at as well as what we call cyber threats. We observe that there's a reduction in acquisition price and in the complexity of running software-defined radios. And we see that there is a proliferation of what we call radio frequency interference. These figures are compiled by Eurocontrol in their voluntary incident reporting. And thanks to Gary for creating awareness here for me. You can see that these voluntary reports from pilots that observe GPS outages in flight have been going up dramatically over the past few years. And so clearly this is something that we're very interested in. A word on the use of the word cyber. Yes, cyber aircraft are cyber physical systems. They are a mechanism controlled by algorithms, and they are there is interplay between physical software, physical parts and software components. They are deeply intertwined. So we have to be aware that that makes aircraft cyber vulnerable. And we think that they really need to be designed with more resilience in mind. And when we talk about cybersecurity in this context, we don't necessarily refer to the classic approach of having IT security and maybe you have strong encryption and access control and that kind of thing. We have been looking a lot more at the radio aspect of it, of securing radio interfaces. So the human threat to CNS is, we have increased ease of access to software-defined radio. The know-how on standardized CNS signals is out there. It's on the, you can buy the standards on the internet. They're accessible pretty much to anyone. And the systems that are currently in use are often designed to be backwards compatible. And so when they were first designed, they were often not designed to be tamper-proof. And that's where we distinguish between safety and security. Safety is when you talk about having protecting for random errors and faults and things that might occur naturally, where you can assume that if you have a fault at some point, it's independent of some other fault that happens at some other point. But when you start talking about security, you need to worry about individuals and people trying to change the way things are operated. And you can no longer assume that one security incident is going to be independent from another security incident. So it's important to look at that aspect of it. And we typically talk about two types of threats. In navigation, we tend to call them jamming and spoofing, and it usually refers to denying service to GNSS or GPS-based services. In the case of spoofing, it's a much more targeted thing. You can mislead a GPS receiver into believing something that isn't true. In communication, they tend to talk more about man in the middle. But it's that notion of purposely misleading someone or something that is kind of scary. About jamming CNS systems, I thought I would say a word or two about that. We wrote a paper a couple of years ago on this topic, and we identified, things that are latent there in CNS systems. For example, VDL2 relies on carrier sense multiplexing. That means before you transmit something, you wait that nobody else is transmitting. So it's like being at a dinner party and you want to say something, but somebody else is talking the whole time and you're waiting for that person to stop talking. They can totally just block you out of the conversation if that is their goal. GNSS, of course, is known for having very faint signals. The satellites are 20,000 kilometers away and they don't broadcast more than some 20 watts. So a pocket-sized transmitter can deny service to large areas. And there are also ways in which, for example, SSR can be jammed if you flood an interrogator with fake responses. So these things are all doable if you have a software radio and if you've got internet access. Does this kind of stuff happen? Here's a NOTAM from Cyprus. Signal interruptions in the Nicosia FIR, dated February 11th, 2020. So this is definitely something that's out there in the airspace. And so we decided to go take a look at this. We took our biggest bird. This is the Diatra. It's DLR's own Airbus 320. And we decided to take a scenic tour of Nicosia FIR. We flew for about 1.5 hours. You can see where we flew in the middle. And on the right, you can see where we actually had GPS available. And you can see it's not a majority of the time. And when you're in the cockpit, it's actually pretty interesting what you do see and what you don't see. This is a challenge in awareness for the pilots. It apparently can be disconcerting. The air traffic controllers at Larnaca Airport told us they have increased number of go-arounds when they see interference events. So I decided to try out this feature that the SESAR webinars provide, which is polling. So we set up a poll. You can tell us. I mean, it's the only way I have of interacting with the audience at this point. So have you ever seen this happen? I'd be very interested if you've seen this happen, in what form. Basically, what we see is that both GPS receivers are faulted. You know, we have loss of primary navigation. I found that pretty scary stuff. However, is it really a threat to safety? Well, it's not an acute threat to safety. The way CNS systems are designed, you have some redundancy. That's what they call the CNS safety triangle. If you lose one of the 3 domains, the other 2 will be able to complement in a way that you can still have safe operations. You do, however, lose efficiency and capacity because you're in a degraded mode. So if you have one domain that is permanently degraded, we would need to be very careful about assessing the safety and efficiency of that. And the people in Cyprus are definitely telling us that this is hindering PBN implementation. How does this translate to communication surveillance? Clearly, these events are collateral to the geopolitical reality, but politics can change much faster than we can change aviation standards. So we believe we need to be very active about this. We have seen no reason to believe that this is an action targeted at aviation. We have looked for spoof signals in our recordings. We have not been able to identify any so far. But we believe it shows that aviation is hugely vulnerable to the goodwill of others. There are technical solutions, and that's one thing I'd like to talk to you a little bit about. We as a research institution propose technical solutions to stuff. It's just very difficult to see them implemented. And in some cases, we don't talk necessarily about solutions, but alternatives as well. And my understanding is that communication and surveillance are definitely preparing for resilience, and I would most certainly encourage them to do so as well, because we see some of these problems in navigation are, I consider them pretty severe. So what kind of technical solutions are we looking at? I just picked up 2 that I think are interesting from the perspective of our work. One is the use of smarter antennas, because if you have smart antennas, you can validate the direction of arrival of a signal. You can reject radio interference by steering your beam patterns. You can do that both on the ground side and the airborne side. And the other thing that we are very supportive of is exploiting redundancy and consistency by having, in communication, they call it multi-link communication. In navigation, of course, we talk about multi-sensor navigation. And basically exploiting any amount of redundancy and consistency that you can. So when you talk about physical layer security, it's actually very useful to have these multi-element antennas. And this is an antenna designed by one of my colleagues, Stefano Gaetone. This is a GNSS antenna, dual frequency, and multi-constellation capable, of course. And what you can see is it has 1 element for the L5 frequency and 3 elements for the L1 frequency. So you can do some of this array processing stuff with it. And on the side of functional redundancy, one thing that we've put a lot of work into is improving the performance of alternative PNT systems in the hope of being able to provide seamless PBN operations during outages of GNSS, which would have been very useful in Cyprus. but also you can check the consistency of your GNSS solution with your APNT solution in order, if you're looking for misleading information there. How can you leverage these multi-antenna systems? You can, for example, do beamforming. This is the sensitivity pattern of one of these antenna arrays. If you're looking, typically you would be looking for satellites right above you. So what you can see here is a sky plot or polar diagram where the zenith is right in the middle and the horizon is the circle on the outside. So in this configuration, the antenna is very sensitive to things that are coming from right above. But if you sense a perturbation coming somewhere on the horizon, you can adaptively steer your beam pattern, and you can try to ignore a particular source of interference, for example. Something else that you can do, which is independent of that, is you know where these satellites should be relative to where you are, because you have a navigation message available, and you might have an almanac from GPS, so you have an idea of where the satellites should be that you're seeing. But you can actually, if you can actually estimate the direction of arrival of your signals, and you see, hey, all my signals are coming from this one spot, and it's on the horizon. Well, that's suspicious, right? So these are some of the technological developments that would really enable a lot more resilience in CNS, or at least in navigation. And the other one that we work on very heavily is improving terrestrial radio navigation. Of course, GNSS, we know, provides unbeatable navigation performance. No system is better currently than GNSS. But in its absence, integrated navigation services are lost. Also, when you talk, Emiliano was talking about integrated CNS, and I kept seeing how GNSS is about to permeate navigation and surveillance even more than it does today. Clearly, this is something that we need to look at in the future. And so we're looking at alternative PNT with integrity, which is still an open problem, but we've started pursuing the effort of making LDAX into a more capable navigation system. So LDAX is a communication system that is currently being standardized. Our colleagues in Communication First showed that you could do ranging functions with this, and in 2018 we had some flight experiments. You can see this is Munich Airport, and this is Oberpfaffenhofen Airport. This is where my office is. We flew around our vicinity. We set up 4 ground stations, 4 LDAC ground stations. We were able to show, at the time we were able to show that we could perform to an RNP1 standard. We are working on RNP 0.3. We believe we have the processing for that now. This is subject of our work in PJ14. So thank you to SESAR for that. And yeah, we're working heavily towards RNP 0.3 in a way that's redundant with and independent of GNSS. So in summary, we talked about how aviation is a cyber-physical system. We need to worry about cybersecurity, of course. Conventional CNS signals and systems were often not designed with cybersecurity in mind, and I think we need to update that kind of thinking. And the disruptions show vulnerability to the geopolitical reality, and I think we need to be very active about making CNS resilient. I really wanted to thank the colleagues that helped me out in putting my presentation together. But I also want to thank the audience for their attention, and Ruben for the invitation.
Okwari, before we go off stage, you launched a poll. What were the results?
Yes, sir. Shall we check?
Yes, please. And what do you conclude from that? That would also be interesting to know.
I have to vote first. So people are still voting, I see. Numbers are changing.
Good. Give it a couple of more seconds. Can you see? You can't see the total number of people that voted, I guess. So we have 200 people connected at the moment.
Yeah, I can't see the total now. I'm seeing a lot more yeses than I expected, especially because we actually discussed it before, just in the round before we started the webinar. I wasn't very hopeful to see a lot of yeses, but I see a lot of no, but I've heard it happens. And I also see some people are completely surprised about this, which is also good. Thank you, Ruben.
All right, thanks. I do see, again, still lots of questions coming in, and we're going to need time for the questions and answers as well. And we still have one presentation to go. Meanwhile, just keep an eye on, see what you can answer already, also for you, Aquari. Again, I'm going to highlight once more that there is going to be another CNS webinar. So it'll zoom in, and I'm just going to highlight it for a moment because I see so many questions coming in at the moment. So there's going to be a topic specifically focusing on the transition from ground-based to space-based, from single function to integrated CNS with a particular focus on LDACs. So there will be more elaboration on that in the next webinar. The evolution towards digital voice, so related to the VHF discussion which we had before. And the last one, not so much touched upon so far, from barometric to geometric altimetry, which is, I think, a very interesting topic. So, Aquari, if you can take your presentation off.
Oh, am I blocking things again?
Well, not again, but yes.
Sorry about that. Done.
So, Gary. Gary is a senior expert in navigation systems, responsible for the radio spectrum coordination at Eurocontrol. He has broad experience in navigation and spectrum standards through his work at the ICAO navigation panels, as well as several EUROCAE and RTCA groups. Prior to the 14 years at Eurocontrol, his work experience include working for SkyGuide, the ANSP of Switzerland, and the US Naval Air Systems Command. Gary, the floor is yours.
Okay, thank you for the introduction, Ruben. I guess I should probably, you see my presentation?
Can you put, yeah, that was presentation mode. Perfect, yes, we see it.
Excellent. So let's get started with spectrum. You see that in aviation, we've made all sorts of progress. You see there the pictures on the right, the various cockpits, and you see they look more modern, more fancy, displays are nicer. On the left-hand side, you see a modern air traffic control system, where previously that was monochrome delays, where you saw the radar beam actually sweep across the display, and you'd only have a little blip update every 8 seconds. What you don't see here in this picture is the kit in between, which connects all of these things, and that's CNS Systems, and they all do that through means of radio spectrum. So this is the unseen enabler for aviation CNS, and of course one of the big questions is how much progress have we made with that? And it depends a lot on who you are and what kind of a perspective you have on spectrum. If you're an airline passenger, you don't really typically think much about all the radio spectrum and the various systems that are involved in making your operation safe. All you want to do is pay as low as a price as possible and at the same time get safely from A to B. That is just something that the passenger assumes. If you're an airline executive, head of aircraft fleet purchasing, well, the moment anybody proposes to put a new box on your aircraft, you have to ask yourself, what's the business case? And if there's not anything new that you can do with the new box, you say, well, sorry, but I don't have a business case. So take your new box and put it somewhere else. On the other hand, if you're the innovation lead of a large telecom company, you say, these systems have been standardized in the 1950s. In some cases, they're 70 years old. You know, my innovation cycles cannot stand you sticking around with old systems for so long. And then on the other hand, finally, the state radio regulator has to balance the interests of a healthy air transport industry in his state with the industry of telecom companies, which in many cases, when they do spectrum auctions, provide very good revenues. So your view on spectrum depends actually quite a lot on who you are. When we talk CNS evolution, as we've looked at in the previous slides, the question is, well, where will the spectrum come from for all this evolution? We have a lot of kit, a lot of stuff in place already, as you see from this very crowded picture. There are different options for growth. One is in-band, so that is the 8.33 kilohertz example, where we took an existing, no, that would be in-channel, where we took an existing channel and we split it in 3 to optimize further use of that system. In-band, a good example there would be GBAS, which goes into the ILS and VOR band. And basically, as VORs are reduced in number, there is space for the GBAS VHF data broadcast. Another option is a completely new band. That was the MLS case, where a band up in the 5 gigahertz range was available and reserved for an implementation. And that, of course, is wonderful because you have no transition issues. Another thing that is difficult quite often for the non-aeronautical industry to understand is that we have under CNS different flavors of things, where certainly the communications world is a lot more alike the telecoms. When you talk about navigation and surveillance, data is not your main product. Many nav and surveillance systems use data, but it's really only a means to an end. And at the end of the day, what you care about is positioning, accuracy, and integrity. And many people don't realize that actually accuracy is also proportional to bandwidth. So you could talk here, for example, about either a data bandwidth or a positioning bandwidth, but we don't really have very good criteria for positioning systems and what makes an efficient positioning system and how you compare that to the big telecom world, where they quantify everything in bits per second. So we tried to study this in SESAR 1. The idea was to say, let's look at whether we can figure out, because we often hear the accusation that we are not spectrum efficient. Let's see if we can actually figure out how efficient or inefficient we are. And then based on that, see where we need to improve, and then see whether we can set priorities on how and where to improve. And we wanted then to test this hypothesis in the L band to make sure that we optimize that one, because that is one of the most contended band, as it is at a prime frequency band in terms of both achievable data rates and achievable ranges. And then to see how we could go further about improving. So LS Telcom did this study for us. They took a comm angle, of course. It's a telecom company. They took the various metrics, which typically is bits per second per hertz, and they had the challenge of, okay, how do you fit a radar into that? And they did a somewhat hypothetical calculation and turned all the little pieces of airspace that a radar could identify into a data rate of 6 megabits per second. So if you start to make such calculation, you get into really what I would call a numbers game, and whether this is really appropriate or not is very hard to say, because in most cases it's an apples versus oranges comparison. Nonetheless, we looked at a few results for typical systems, where actually some systems were not doing so bad. LDAX is one of these examples, and then some of the more traditional aeronautical systems are lagging a bit behind, whereas other systems are also in similar ranges in the comm world. Certainly some systems achieving quite good scores, others not necessarily. The question is, how do you take that further? And we tried to see, well, given that we have to supply aircraft that are flying in huge portions of airspace, well, how do we consider the spatial dimensions, so bit per second per hertz per kilometer square? And we then saw that the normal metrics that are used in IEEE or in ITU, they're actually trying to optimize the data throughput for a given area. And they're not trying to size the right size to level of service to meet the required demand. In navigation, if I need to just be able to position myself and a certain number of aircraft in a certain area, being able to position more aircraft or position my aircraft more accurately than is required doesn't actually give me anything. And so also, even when we talk about what we thought were relatively simple metrics. Is bit per second the transmitted data rate? Is it the useful information payload after error correction, etc.? When you talk to hertz, is it really, what kind of bandwidth are you talking about? So there's a lot of questions that you can ask, and you find out that actually spectrum efficiency is a lot easier to compare when you is a lot more, special efficiency metrics are a lot more useful when you actually look at an individual system or a very similar system. When it comes to systems that have fundamentally technically different characteristics, that is very difficult. So unfortunately, our underlying study assumption that we could use metrics to derive priorities for where we should improve didn't really lead to the conclusion that we wanted, and we still don't really have suitable metrics for spectrum efficiency for CNS systems. I'm still doing further thinking on that, but and would like to study that more from a telecoms point of view, but this is where we are. One interesting finding was that actually adding data to DME did not provide a very significant data rate, that LDAX actually does a lot better, provided we can accommodate that, and that is currently under study. DME and LDAX compatibility studies are ongoing currently. It could, of course, be interesting to add data to the DME service, but that would be more to improve the DME service, just like GNSS has data on it to you know, have some ephemeris. We could, for example, code the DME station data on it, and there have been approaches that were proposed, such as having a passive ranging approach and such. So that was a key issue for the L-band, but more generally, we tried to say, okay, well, can we do better in how we use the L-band? And the study looked at a very simplified version of providing DME coverage, but it looked at doing this on a cell-based planning method, and it figured out, without siting constraints, and it figured out that you could do with 50% of the channels that we are currently using. And then the other thing that they did is they said, well, what would be needed to provide all of the CNS services using state-of-the-art technology? And of course, you can argue the calculation and you come out with either 10 megahertz, 20 megahertz, 40 megahertz, but we just wanted to put a number out there to say, okay, well, what is the number that comes out of that? Well, when you look at these 20 megahertz compared to the over 200 megahertz that we are using, then yes, of course, if we could do a clean sheet approach and start all over and not have any past investment that we would need to be concerned about, and have you know, infinite resources in terms of new system developments, then of course that would be fantastic if we could do that. What we are doing with that, rather than a full radical transition, we are looking whether we can do a soft transition. So in the Spectrum, in the ICNS solution project that Emilien talked about, we will see whether we can replan some DME channels, given that we take out a few VORs so that the pairing constraint goes away, and we're evaluating the feasibility of freeing up a portion of the L-band spectrum to enable a new technology transition. Unfortunately, as you see here, the L-band spectrum is already very crowded. And there's much sharing going on already. And you see the channel pairing of the interrogation and reply channels of the DME, and you ask yourself, well, so if I can free up some channels, where should I free them up? And you kind of say, well, I don't really want to touch secondary surveillance radar, and probably not what is in between. So that then leaves either the lower part or the upper part. Well, in the lower part is where we accommodate LDAX, where we already have JTIS mids. Similarly, in the upper part, if we take this away, we sort of expose the sharing partner. So GNSS will, of course, benefit. Right now, GNSS needs to implement pulse blankers, and they cost the receiver a good 8 dBs, 9 dBs in power degradation of the link budget. But you take the DME away, then the question is, what else will want to come in there? So there, it's really a complex band where if you start to look at the details, it's very challenging to actually identify a feasible roadmap. And that's really all we can say at this stage. I think we're not doing enough to study this topic. We are sometimes too busy with just given the resources available with plain spectrum defense. And in the CNS evolution project, of course, we need to look at how we can transition to something that is also more spectrum efficient, because to have a continued access to safe and interference-free spectrum actually requires that we become more spectrum efficient. What we know is that we have a very diverse mix of analog and digital systems that are hard to accommodate in single bands. We also have learned that space-based technology still require terrestrial backups and that we need to work within the existing allocations. Like I said at the beginning with the picture of the different systems, we have a mature industry. We know how to bring people from A to B at high speeds, fairly efficiency at a low cost. And that also means that it's very hard to do anything fundamentally different, fundamentally new. And of course, we still have an open market that is driven by individual stakeholder business decisions, and actually harmonize something here is very challenging. What we do need to focus on is that we combat common mode vulnerabilities with common mode strength. Okuwari talked about some of those possibilities. Most of all, we have to stop taking spectrum for granted. I quote you two numbers there. 150 billion is what the European Commission will invest into the digital economy over the next 7 years. In a similar time frame for ATM research, we spend about 3 billion euros. The portion of that we spent on spectrum matters is maybe 1 to 2%, whereas of those 150 billion euros, about a third of it goes directly in the 5G. So these are numbers that will talk. When you look at the difference in investment and the dependence that aviation has on being able to use interference-free spectrum in order to operate, well, clearly we have to stop taking spectrum for granted and we have to do more. And that is also because we have new entrants. We have CNS evolution, where we need to talk better between ComNav and surveillance. We have RPAS coming in. We have security requirements coming in. We need to continue to accommodate military and state operations. So this is a formidable challenge, and it keeps us entertained. So I'm looking forward to your questions.
Thank you, Gary. I'm also looking forward to questions specifically on your presentation, because to my big surprise, they're actually not there. I suspect that it's because you are the expert on spectrum and no one else is, which is maybe a bit worrying in itself. I would like to invite the audience to ask any questions specifically on spectrum. And when we go to the questions and answers, I'll give that a bit of time. So I'll first go to some other topics before we come back to spectrum to see if there are any other questions coming in on this topic. Let's see, we have 20 minutes left. So let's see how far we can get. So the first question coming in on spectrum, that's good. I'm going to start with incentivization. I'm starting off with a very difficult question here, so get ready for that. I'm not sure who. I guess Emilia, maybe it would be you, but I'm leaving it up to anyone else. So it's Thomas Buchanan here. I guess a bit triggered to the previous webinar, actually, that was on the evolution of ATM data service providers. So when you look at the rationalization, what incentive do you foresee for the ANSP or the state owning the system to give it up or to shift to a different location? There was another one related to it, which I don't see so soon, about a single service provider for infrastructure. I think you also answered that one, Emilia. Maybe you can have a slight word on incentivization and where you think this is moving.
Well, I agree, and I thank you, the audience, for raising these questions. Rationalization has an initial cost, indeed, and it needs to be further tackled. For now, I am not aware of any specific incentive. It's mainly based on business model, on cost-benefit analysis, with the idea, and when you rationalize in the longer term, you can also save some costs. We can fund your initial rationalizations, but it is a subject which needs to be better discussed in the CNS and ITM community, indeed.
So something related to this, Emilia, I guess still for you, because you referred to it in your roadmap. There is a reference to the minimum ops network, where Claude Pichafon says that the devil is in the details. If you refer to the current GNSS performance SARPs, the minimum is actually not sufficient.
Yes, indeed.
I think this is answer to that.
Yes, indeed. But by minimum operating network, we don't really provide a figure for each technology and for each system. It will depend from case by case. For example, if you think about DME is the system for at least the short-term to mid-term IP&T, backup to GNSS for positioning. In that case, the minimum operating network will be mainly an optimization of the current infrastructure that we have today. And Gary can elaborate on that particular example. In other cases, it would be a much stronger rationalization. If you think about NDB, that would be a much stronger rationalization. Well, I think one very good example of this minimum operational network is what happened in France in the last few years when the network of ILS Cat1 has been rationalized. The idea was to replace some of the ILS Cat1 service by SBAS-based approach, EGNOS-based approach. But we are keeping a certain number of ILS Cat1 in place, so that to ensure that for every airport on which you would like to land in a Cat1 with a Cat1 procedure, you can have another airport equipped with an ILS within less than 1 hour of flight, or maybe it's less than that. But there's kind of a distance with that. So the idea is not to remove all the equipment, is really to have a fair rationalization down to a point where your infrastructure supports the backbone of future infrastructure in a way or another.
Thank you, Emilia. You did mention that Gary wanted to add something, but I saw Gary typing very focused. So I don't know if you spotted where you were suggested to add an example. Did you hear that, Gary?
Yeah, I heard, but help me, Emilia.
I was talking about minimum operational network and what it means, and I was mentioning that, for example, for DME, it could be more of an optimization of a current network rather than a strong rationalization for now, because DME is foreseen as the short-term to mid-term IP&T.
Yeah, there were time studies a few years ago that said we needed like 20-30% more DMEs. In the meantime, we've done, in the first generation of SESAR, we've done new studies and said actually we can live with the current number of DMEs. We just have to optimize their placement. And also we found out that we can support a rationalization of VORs down to about 50%. And still provide a very reasonable minimum operational network that supports state aircraft and general aviation.
Okay, thanks, Gary. I'm going to a different topic. Moving on to voice. We touched upon that in the beginning, so I guess these are going to be, at least as a first instance, for Esther. So I see two questions here, or actually there are three related to voice. So I'm going to ask them all at the same time, so see how you can answer them. So the first one is from Xian, how to use satellite VHF voice. So that's the first, because we don't have it at this moment. Then the second one from Ibrahim Kozanli is, are there any KPIs or quality of service defined requirements, I guess, defined for satellite VHF voice? And then the third one, I'm going to ask that straight with it, which may be more for Gary, I don't know for sure. How will we find VHF spectrum for satellite VHF in Europe and in the vicinity? Would a digital voice system not be a better long-term solution? knowing that we're going to have a different topic on that later on. Esther.
So, well, new initiatives are emerging for the use of the VHF voice, but they are mainly for the oceanic use, and the oceanic carriers are still being developed at this moment. So there are no quality of service or requirements yet. But well, it as well as I mentioned VHF satellite, but it could be also other technologies that have some requirements of VHF like. So it hasn't to be VHF satellite communications. It could also be enhanced SATCOMs or, for example, LDACs. But I think that you should come to the next webinar for the CNS webinar that will be more focus on this topic, and probably it will solve the doubt that the people is having now related to the communications and the satellite-based communications.
Okay, thank you, Esther. Gary, do you want to add anything on this?
Yeah, you know, Akori talked about, and also Emilien, how we have by now quite a broad cocktail of different technologies that we're using. It's actually for any individual quite difficult to even keep an overview. You've seen how densely packed Emilien's and Esther's slide were. You know, we have a comm evolution in the VHF band. We have a candidate comm technology in the L band. We have SATCOMs at various frequencies. So it's actually quite difficult to balance all that and actually clearly understand what user needs are. And that's really at the end of the day what counts is what are the needs of the aircraft operators to ensure safe and efficient services, and to translate that into specific bandwidth evolution needs. So that's still a very much an ongoing topic of discussion to try and align what we can do technologically while we have many good ideas with what the industry is actually willing to implement.
Okay, thanks, Gary. Since we're now here with you on the spectrum, I think by now it's, although exactly as I speak, there is a new question coming in. I thought it's been stabilized, the number of questions on spectrum. I want to open that topic on the discussions. So I see a couple of things coming in. So first of all, a very easy one. By suitable spectrum, you mean safety of life spectrum. I think it's a bit related to one of the others. What is your position on designing C-bands for 5G for aviation usage? So also linking it back to the topic of new entrants, I guess, the drones, the U-space, which are actually using commercial spectrum and not safety critical spectrum. Where does this go?
Yeah, so we, you know, have of course done well with our safety spectrum. You see the current challenges that we face in GNSS, which is safety spectrum. So even the base RNSS service is a safety allocation, and its aviation use definitely is a safety use. But of course, the moment you have a service that is provided by satellites from space 20,000 kilometers away, you have physical realities that you have to deal with, and then there's the geopolitical realities. So actually, that makes it difficult sometimes if the goodwill among states is not there to really ensure safety of operations, even if the spectrum is designated safety spectrum by ITU. So that has a treaty status, but international treaties are at the end of the day soft law and will really hold up in accordance with the goodwill of the states involved. For terrestrial safety spectrum, that has worked quite well. Of course, you have new entrants like 5G that want to offer new services, and you have the argument from the telecom companies that says, you know, if I have a large pipe with a big bandwidth, and oh, you aviation guys, you just need a tiny fraction of it. Well, you know, I just put in 3-4 redundant channels. That's still not much data for me, and there you go. You can have a service, and that'll be fully redundant and safe. While that is an argument worth thinking about, we do struggle with commercial operators for them to actually sign up to the type of service guarantees that typically the air navigation service providers require to be able to provide their services. It's just as Aquari has shown on his GNSS outages. When you talk to an air traffic controller and to a pilot, whether he wants his system to work 99% of the time or 95% of the time, the answer is always 100%. So it needs to be some value very close to 100%. And if you cannot ensure that with a single system, that really means that you need a fully redundant dual system, and that is not spectrum efficient if you need to do the same thing with 2-3 different systems. And that's really the trade-off that we currently have to look at in our projects.
So actually, I was intended to stop the topic here because we're running a bit out of time. I do see two very technical questions, the last one that they came in. I think I'm going to skip those for now. I think it's better that you answer them online specifically because otherwise there's not enough time to look into the other questions. I do want to touch just for a moment, I'm not sure who to ask, may also be Emilian here, I guess, about using commercial spectrum for safety critical services or for aviation services anyway. So instead of having, let's say, dedicated spectrum, there's also the principle of having spectrum sharing. And if you add to that the mechanism of prioritization, I could imagine that if you would prioritize safety critical services over anything else, you could do that in a shared spectrum environment. Is there any evolution or thoughts going on that? Emilian, I see you moving.
Yes. Sorry, I was on mute to ensure there will be no noise. I believe it's more a question for Gary. I'd be happy to support, but I think Gary will be in better position than me to answer this question about spectrum.
Back to you, Gary. I see you're good friends.
Yeah. Yeah, and by the way, there are plenty other experts besides me. Some of them are actually in the audience. So, like I wrote, we haven't proven yet that we really can make it work with non-safety spectrum. And while for the drone community, the going in position is that they will just use commercial spectrum because they're very commercially oriented. The similar situation is there for the automotive community that is looking at autonomous driving, which also all in some flavors with various levels of dependencies use GPS and GNSS, multi-constellation GNSS, using every signal that's available, augmented by many other things. So the GNSS community has had to learn that, positioning really means integrated navigation, where you take all the various assets that you have and use them to your best advantage. And then the question is only how much of an outage can you really tolerate? And the difficult thing is really when you have drivers to interrupt. You have that, for example, with road tolling, with privacy concerns, with concerns about drone warfare. There you have drivers to interrupt. And I think as long as you have drivers to interrupt spectrum, it's pretty much impossible to offer safety services in that spectrum. So what you have to do is have to ensure that that spectrum remains free from any drivers to interrupt that spectrum. And that goes down to how you actually design the service, where the moment you make your service very vulnerable to an interruption, you also become very attractive to interrupt. I realize these are quite generic answers, but this is the stage where we are. These are difficult questions to answer.
Okay, I think let's leave it to this one. There are plenty of more questions that could easily connect to this.
There's one question with 9 votes.
Is there? And it's probably related to you, I guess.
No, it's not. It's. I
Oh.
think it's a question to Gary again. I thought it was pretty interesting. Konstantinos Simayakis.
So now 10 votes then, I guess. So each and every state is legally liable for traffic being carried over, carried out over its airspace. With the introduction of GNSS, how the liability issues that inevitably arise will be addressed. I'm not sure Gary is the right expert here, but maybe you want to give it a try.
Yeah, I actually did a study with a legal colleague on this. So this is not my Spectrum hat. This is my GNSS hat. Basically, anytime an ANSP uses an external service, really the only way to make sure that that external service is really working right and to take measures when it's not working right is to monitor it. And that's why we foresee monitoring provisions. So for example, as long as the Russian Federation, the United States of America, the European Union, and the People's Republic of China, commit in the ICAO Annex 10 SARPs to provide the services that they've offered to provide to aviation with GNSS, then that is their commitment. And if we monitor their commitment and see, they're actually holding up their commitment, then we can use those systems safely. What many people don't realize in the liability chain is where it actually starts, right? The moment you have an accident, you start with the victims. And the victims will typically sue the aircraft operator. The aircraft operator then has a chance to seek regress from whoever he thinks is at fault. And the way it typically works in liability law is that you go after the biggest pocket. Fortunately, we actually have a very good safety record such that there's no case law history on this, which even in Europe plays a role. It's not just in the US legal system. And so because you don't have any case law history, because we haven't had such accidents where an external service used by an ANSP was responsible, we also don't know how this will play out. So rather than worrying too much about the legal issue, for which there are some answers, ICAO has issued some guidance, but it's also arrived at a bit of a stalemate in the legal panel on GNSS, despite there still being assembly resolutions on this. There's not going to be too much progress. But one of the great things that we're doing with introducing multi-constellation is we're at least alleviating one concern, which is on sovereignty, because we are no longer dependent on one single GNSS system called GPS provided by one state. So with that, we're really reducing our dependency, so that alleviates the sovereignty concern. And we're having a lot more of a robust GNSS system that is even less likely to be at the root cause of an accident. So hopefully we can skirt around that despite the limitations in the international provisions.
Okay, thanks, Gary. That was a very elaborate answer. Before I wake up Okwari again, because I see that he's very keen to speak, but yeah, you are.
I was very keen on hearing an answer to the question. I'm sorry if I...
No, it's fine. But
I thought it was really
you'll
a question.
get your turn. But we're running a bit over time, but I'm going to continue for at least another 10 minutes, I think. However, I do realize, actually, as you were speaking, Gary, that I asked Esther to remove a couple of slides on surveillance performance monitoring. And I think that you were actually referring exactly to monitoring performance. Esther, I'm going to give you the floor. See if you want to add anything on that, particularly on the work that is ongoing in SESAR. You need to unmute. Yeah.
So in SESAR 2020 Wave 1, we started to work on surveillance performance monitoring tools. And in this wave, we are keeping the work in solution 84. And basically what we are producing is 3 different tools. Eurocontrol is working with SASI. Thales is producing MAX. And Indra has been working on its own tool, which is called ACCPOD tool. And these tools are are surveillance performance monitoring tools, which seek to identify degradation trends early using both offline and quasi-real-time processes. And what we are doing in SESAR is to test the 3 tools against the same scenario and try to see if we are obtaining the same results in order to have the independence of use from one tool to another. That's what I wanted to explain.
Okay. Thank you, Esther. Okay, let's move on to Okwari. So you've had your chance to warm up again. I don't know if you have any clue which direction I'm going to go. It's about cybersecurity, not a surprise, I guess. I see 2 compliments for your presentation. I actually saw a lot of good feedback on your presentation. People are really happy that you're addressing the cybersecurity issue, not just from a digital perspective, the bits and bytes, but in particular on just the radio waves, I think. And there are a couple of questions coming here. So first of all, I think, again, this relates a bit to the fact that this is not just about the bits and bytes. So Thomas Buchanan asking here, will you reuse existing standards from the banking or other domains? So that's one. I'm going to group a couple together before you start answering. The second one related to this is, I think, from Robert Westerberg, regarding the plan to consider the cybersecurity elements, building on the question from Thomas. How will this work be undertaken and what standards will be used? How do we ensure that the resulting cybersecurity is and remains robust in the face of an ever-changing threat landscape? And then the last one, how do you expect to force users to invest additional features? But that one is a more complicated one, I guess, because this is basically about when is it going to be good enough. But looking at the other questions, I think, and maybe this one. Since you're not only looking at the digital stuff, what do you think is the human role on this in the system monitoring control when you look at spectrum performance assessment? So from Kostas. I think that's it. Your turn.
My turn. Thank you, Ruben. Thanks for the questions. These are really interesting. The first one was there were a couple of them that were about reusing existing standards. That relates a lot more to the sort of classical view on cybersecurity and IT security, data security, encryption, authentication. I personally see no problem in reusing existing standards with that, but aviation has a way of working that it will probably require its own standards and standardization processes. Those are data level questions that I'm not well prepared to answer because we have looked at the issue a lot more from the physical point of view of, as you were saying, Ruben, how the radio waves come in. I personally see no problem with reusing existing standards and systems on the data level security. But Ruben, maybe you have some more insight on that. You have a different type of expertise in cybersecurity.
Well, I think that like on the digital side, we are, well, first of all, the cybersecurity aspect has become a transversal aspect that has to be addressed by all the SESAR solutions that are being developed. So we have, let's say, a general cybersecurity risk assessment methodology, which is not very different from the ISO approach. And actually, there is a tailored EuroCase standard being developed on it on the same direction as well. I think we could spend a complete webinar on cybersecurity, I guess. We're not going to do that now. But I think that the biggest challenge that I see on managing cybersecurity is the fact that cybersecurity management has many different elements, some of which are actually quite sensitive, and we don't want to have that in the public debate. And it requires a trust framework to share, for example, information on actual attacks, on vulnerabilities in systems. And I think similar to a safety management system, the only way we are actually going to move forward on that is by finding some way to share that information. Now, that is work that's ongoing. And one of the things that is being discussed at the European level, so the ESCP is working on that, is to understand how we can move forward and that instead of each of us protecting our own vulnerabilities, not sharing it. We've seen that it's possible because we know that it's working with safety management. We have a global safety management system. It works. We're sharing information, and that's where we need to go with cyber as well. I think on the radio waves in particular, so not on the digital side, we have a couple of exploratory research projects. So we actually touch upon that query. But I think there's still quite some work to be done.
I would love to see an effort to put array antennas on airplanes.
Yes.
Nobody wants to pay for that. Hint, hint.
Yeah, so here we come, and I guess it's time to move on to the next topic. There are a couple of questions still left, and let's move on to incentivization. I think, so you're touching upon one query, which is about what is the incentives for actually securing your systems in the future. I think I'm going to look probably at some point at Emilian, because this touches upon the roadmap, like how are we going to move forward actually. And it also links to the discussion we had on spectrum, like if we're trying to, for example, free up spectrum for safety critical services for the new entrants, not for the commercial aviation that we know today, who's going to pay for that? If we need to rationalize infrastructure that we don't need anymore because we have to free up for other uses, how are we going to incentivize that in such a way that the stakeholders that are going to be impacted have a positive business case along the line? So who dares to speak up on that? Because it's a complicated question, I think. And I am looking at you, Emilia.
Thank you. I captured two questions, and your question was about a practical step towards cybersecurity. The second one is about incentive on rationalization. For the first one, I will have some difficulty to answer right now. The idea is more, the idea of a roadmap on the first edition of its roadmap was first to identify the need for a more a more secure environment. We are moving from a fully open system to our more digital systems, and at one point, cybersecurity needs to be tackled. Now, having said that, in the project developing a roadmap, the idea is to capture the content developed by other solutions or by other initiatives or by other groups, and to include that into the next edition. So actually, if we have a webinar for the next edition, I will have more answer to you than now. But as on cyber, I would prefer to come back eventually to questions at a later stage after a small chat with our colleague in your control working on cybersecurity.
Okay.
For the incentive and rationalization, I think we already tackled that question some time ago. In this webinar, I was saying that indeed rationalization has an initial cost. However, the objective of rationalization is not to rationalize for the sake of rationalizations. The objective is to rationalize to decrease in the mid-term to long-term the overall cost of the infrastructure. So far, we are mainly being added layer to layer in CNS, and the idea is to find a right balance with the right level of redundancy, so that we have the right level of cost for the systems. So the whole concept of rationalization is at the end to reduce the cost. Now, how to cover the initial cost? For now, I'm not aware of any practical incentive at European level. However, this is a question that should be tackled. Indeed, it's an open question. And for now, it's mainly covered by the reduction in costs in the mid to longer term.
Thank you very much, Emilia. I do realize that, and I actually do that throughout most of the webinars. I ask the questions that should not be asked because we don't have the answers always. But I think it's also fair. We're a research organization. When you are trying change, when we're aiming for change to optimize something to come to a future vision, we do not always know all the steps along the way. This is why we're doing research. And I think this is exactly why the style of all these webinars is to be transparent on the fact that we are moving forward and still investigating things as well. So I appreciate all of you standing up. I think looking at the time, I think we have to round off. There are still plenty of questions left, which I would invite you as speakers to look into after this webinar to answer them offline, and we'll publish them on the website later on. We do need to end here because I also see too many people dropping out now. So thank you very much for speaking up, all of you. Thank you, audience, for having listened in from all over the world. I actually realized that in the beginning I forgot to welcome both Australia, New Zealand, and also Africa. We had someone from Africa listening in as well. So thank you very much for listening in. I hope you appreciated it. Our next webinar will be in 2 weeks' time on CNS again. Have a good day.
Yep. Thank you so much,
Bye-bye.
everyone. Bye-bye.